So if you open the data book contents, you will have the first chapter like thing is the property values, where you have properties listed for different materials, metals, alloys, metallic solids, and so on. Then the next chapter is conduction, where you have steady state conduction and transient conduction. Then chapter of radiation, followed by convection, then heat exchanger and mass transfer. And also there is an appendix where there are some properties of some special fluids, which if needed we will refer to. Okay, so this is how this particular data book is organized. Currently, what we are looking at is page number 52, 53, and 54. Now I will take you to the slides that we are seeing. So in the last class, this is what we have seen. Um, we have made ourselves familiar with this concept of thermal resistance and electrical analogy. So whatever heat has to be transferred is offered some resistance by the material property itself, which in this case in conduction is the thermal conductivity as well as the thickness of the material. So that becomes a key. So we have seen that in conduction, if we look at the electrical analogy, this thermal conductivity resistance, conduction resistance will be L by Ka. L is the thickness. So here this is L. K is the conductivity of the material and A is the area. So you can see from this formula, you can see that larger the L, that means larger the thickness, more resistance will be offered. Larger the conductivity, lesser resistance will be offered. Larger the area, lesser resistance will be offered. That means if you want to conduct more heat, then you have to reduce the thickness and increase the conductivity and increase the area available for conduction. Similarly, for convection, we have seen that the resistance formula is 1 by HA. So here we have seen this example of a slab which on either side is subjected to convective conditions. So in this you can see that this convective condition offers a resistance symbolically represented like this, conduction symbolically represented like this, and another convection symbolically represented like this. So these are represented as three resistances offered for heat to flow between the extreme temperatures. The extreme temperature is T infinity 1 on the left hand side and T infinity 2 on the right hand side. So this is T infinity 1 and this is T infinity 2. T infinity 1, from this graph I can tell that T infinity 1 is greater than T infinity 2, therefore the heat transfer will take place in this direction, and for this heat transfer to take place there are three resistances to be overcome. This is what we have seen in the last class. So since these resistances are in series, we can add them just like we do in electrical technology. Similarly, we have seen about radiation resistance, and we have also seen how radiation heat transfer can be calculated. Then we came to composite walls, where not just one slab, but a series of slabs placed next to each other. So you can see here we have three slabs placed next to each other, and each of these three slabs, here you see there is this common surface. As of now, we are assuming that this common surface doesn't offer any resistance for flow. That means this surface has a perfect contact. That is what is assumed, but in reality it is not so. Okay, so in this case you see one composite wall having three slabs arranged in series, and here there is another composite wall where this and this slab F and slab G are in parallel, and they are in series connected to slabs E and H. So how to represent these using electrical resistance network we have also seen. So similarly, in case of this same slab, but if there is a convection environment on the either side, we will have this kind of a situation. So here we have totally 5 resistances, 3 resistances, conduction resistances belonging to the 3 slabs, and convection resistance on the left, convection resistance on the right. So all these things have come into picture in this particular representation. So all these resistances are shown here, means the total resistance. So in this way you can calculate the heat transferred, you can also calculate the temperature at different locations. For example, you can calculate the temperature, this temperature we assume it is known, so we can calculate the temperature at any unknown point in between. So here we see two resistances in parallel. So when two resistances are in parallel, what happens is the amount of temperature drop across them will be the same. The temperature drop across slab 1 and slab 2 is same as the temperature drop across slab 2 and slab left side and slab 2, left and right sides of slab 2. So you can see here the left side totally is at a temperature T1 and right side is at a temperature T2. But what happens here is because of the differences in the conductivities, the amount of heat passing through this slab will be different from the heat passing through this slab. So that must be taken care of. So if we do that, the total resistance when two slabs are in parallel, the total resistance will be R1 R2 by R1 plus R2. So this again follows from the electrical network. So here we see a much more complicated thing. There are network of series and parallel arrangements. In this case, you can see these two are shown to be parallel. So from electrical technology, again, we know that we can combine this into one and treat that to be in series with this one and this one. So ultimately, we will have three resistances in series, which is one simple way of solving this. But there is also another way here. You go through this and try to figure out how this has been represented as this sequence of resistances. Similarly here. So this is what we have seen in the previous class. Now we'll go to the next topic called as the overall heat transfer coefficient. See, when dealing with resistance, radiation, we have seen radiation heat transfer coefficient. Radiation heat transfer coefficient is not really a radiation concept, it's a convection concept. Similarly, here you see overall heat transfer coefficient, and we are talking about a system involving conduction also. You see here, these three slabs, they involve conduction, but we are talking about heat transfer coefficient. Heat transfer coefficient, the word we first came across in convection, but during conduction also we are bringing out this. The reason why we bring this word heat transfer coefficient in conduction and in radiation is because of its simplicity. See, the equation which uses the heat transfer coefficient is the heat transferred is H A delta T. It's a very simple and something that makes a lot of sense. So we want everything to be in this form. Therefore, we are kind of fascinated, or we have a liking for this H value. So we want to estimate this. So in the case of this particular arrangement where there are three slabs in series, three composite slabs in series, and a convection environment on the left and convection environment on the right, we would like to simplify this using this concept of the overall heat transfer coefficient. When we say overall, I really mean overall. That means from this point to this point. So if this entire system, if I can calculate the total heat transferred using the equation Q is equal to H A multiplied by delta T is T infinity 1 minus T infinity 4. If I am able to calculate this, then this value, this H value is the overall heat transfer coefficient. Heat transfer coefficient, shortly written as HTC. Okay, so we would like to find what will this value be. Okay, so you can see here, I try to write the heat transferred as a Q with a subscript X, so showing that the heat is following in the direction of X. This is the X. So the general rule is total temperature difference, that's overall temperature difference. T infinity 1 minus, again this is not T infinity 2, this is T infinity 4. T infinity 1 minus T infinity 4, that's overall difference, divided by the total resistance. The first resistance because of convection, second, third and fourth because of these three slabs that we have here, and the last resistance is because of this convection. So all this put together we have. So this we want to write in terms of this equation, where you see a new symbol here. So this new symbol is called as the overall heat transfer coefficient. So we say H, we use H for simply heat transfer coefficient, but for U, we call it as a overall heat transfer coefficient, but its meaning is similar to that of H. So if you equate this with this, then you will see that the value of U is 1 by the total resistance multiplied by the area. Okay, so something involving this term. So you can see that 1 by H1A multiplied by the area. So A gets cancelled. So what you have here is this formula, 1 by H1 plus LA by KA plus LB by KB plus LC by KC plus 1 by H4. Here there are only 3 composite slabs, so therefore only 3 terms. For example, if there are 100, then there will be 100 here. So you will have to account for all of them in the same formula. Okay, so we have this this particular arrangement shown in page number. Open your data books. In data books, the page number 53. In page number 53, the last equation. You see there are 3 composite slabs. Each slab has got thickness L1, L2 and L3. The left side temperature is TA, right side is TB, and there is convection environment. In such a case, you are given one equation for R. R is the resistance. So R is used to calculate the total resistance, and using the total resistance in this formula, we can calculate the value of U. Okay, so you don't really have to memorize these things. They are available in the data book. You must familiarize where these equations are available. So you must be able to readily refer when necessary. Now coming to another geometry, which is called as the hollow cylinder. Now remember, earlier we have seen one similar geometry called as a cylindrical shell. What is the difference between a cylindrical shell and a hollow cylinder? Hollow cylinder and a cylindrical shell. Can you tell me what's the difference?
The one has thickness, the other doesn't have.
Thickness will be there, but in the cylindrical shell, the thickness is small. A hollow cylinder thickness can be large, but technically they are same, okay, except for the magnitudes of the thicknesses. That's all. Okay, so what we have done in that treatment, if I can go back to that slide, here you see the cylindrical shell. What we have done here is we are able to come up with the heat transfer equation for a cylinder in this fashion. So ultimately this is the heat transfer. Now if we can write this heat transferred in the form known to us now, or we are now familiar with it, T1 minus T2 divided by 1 by 2 pi KL logarithm of R2 by R1. Okay, so this is the basic equation of the form. I am writing it like heat transfer is equal to total temperature difference or overall temperature difference divided by the resistance. The resistance here is 1 by 2 pi KL log of R2 by R1. Likewise, in the case of this cylindrical shell also, you can see, now in this cylindrical shell arrangement, you can see there is a cold fluid on the outside. Is there a cold fluid on the inside? Yes, there is a cold fluid in the inside also. See, something is flowing through the center. So this is like a pipe through which something is flowing. So there is a cold fluid inside, and in between there is a solid surface. So this outside fluid offers convection resistance, the solid surface offers conduction resistance, and the internal fluid offers convection resistance. That means there are 3 resistances. The leftmost temperature is T infinity 2, and the rightmost temperature is from here to here, or T1. Yes?
Sir, you just said that there are 3 types of temperature resistance, no, sir. Can you just repeat again what those 3 are?
See, just imagine this particular cylinder, you are able to see this, no? So over the cylinder there is a fluid flowing. Okay?
Yes, sir.
And the cylinder wall has certain thickness. and there is a fluid flowing inside the cylinder. Okay, so the outside fluid offers some resistance for heat flow. This wall offers conduction resistance for heat flow, and the inside fluid offers convection resistance for heat flow. So these are the three. So outside convection, wall conduction resistance, and internal convection resistance. Okay.
Yes, sir.
So we have these three heat resistances. So inside is T infinity 1, outside is T infinity 2. If T infinity 1 is greater than T infinity 2, let us assume that, then we will have heat transfer flowing from the T infinity 1 to T infinity 2. So we have to account for these three resistances. So firstly, we have to account for the internal convection resistance. So this is 1 by HA. You know, the convection resistance is 1 by HA, where A is the inside surface resistance. So it's not pi r square, but it is the circumference multiplied by the length. So 2 pi RL is nothing but A in the inside. 2 pi R1L, because R1 is the inside radius. The next resistance is because of the wall. So this wall brings this resistance. Similarly, outside convection brings this resistance. Okay, so three resistances are accounted and they are all in series. So to calculate the heat transfer, we can write it as a T infinity 1 minus T infinity 2 or T infinity 2 minus T infinity 1. Only thing is you will get a negative sign if the T infinity 2 is greater than T infinity 1 here. Okay. This is the overall temperature difference. This is the convection resistance, conduction resistance, and convection resistance. So all three accounted for, and A1 is written as 2 pi R1L, and for A2 you see 2 pi R2L. So inside surface area and outside surface area are different. So this is a curved object. So unlike the slab, whose surface area at the inside and outside are the same, in the cylinder and in sphere also this thing will change. So that you must be careful in looking at. So you have this composite cylinders in page number 54 in data book. You have composite cylinders in page number 54. This similar equation, you may not see the exact equation because the notation is slightly different, but the notation, the figure and also the formula are given in that. So you can see that this particular equation is available. In fact, not this equation, but the equation for the total resistance is given. So once you know the resistance, you can calculate the heat transfer. The next is again a hollow composite cylinder with a more number of resistances. Here you see there is only one wall, but here there can be several walls. You see, a typical example is that of a pipe carrying very cold fluid. So there is an engineering name for the extremely cold fluids, in refrigeration systems, where you have to store and pass fluids at extremely low temperatures. Cryogenics, cryogenics. So in such cryogenics, you need to isolate the fluid which is extremely cold from the atmosphere. For that, you may have to use a very large insulation or different layers of insulation. So you can imagine this one. Let us say here the cryogenic fluid is there. This is the wall of the pipe through which the cryogenic fluid is flowing, over which there is a one layer of resistance, one layer of insulation, and there is another layer of insulation wound upon the cylinder. So this becomes a composite cylinder, and since inside it is hollow, it's a hollow composite cylinder. So composite cylinder because it is made of three different materials. This is a metal, this is a insulator, and this is a different insulator. So three different materials, and a fluid is flowing inside. There is also fluid flowing outside. So this is the fluid outside. T infinity 4 is the temperature, and H4 is the heat transfer coefficient. And there is inside there is some fluid flowing. So T infinity 1 and H1 are its parameters. So there are two fluids involved and three surfaces involved. 1, 2, 3. So in this figure also you can see 1, 2, and 3. So in this case, unlike the previous problem only had one wall thickness. Here we have multiple wall thicknesses. So even now it's not a complicated problem. You have to take care of the convection resistance inside, like this. Then the first convection here, first conduction resistance, second conduction resistance, third conduction resistance, and the outside convection resistance. So all five have to be taken care of. So you can see these are the 5 resistances, and each resistance magnitude is written here. So convection resistance is again 1 by HA, and convection resistance is 1 by HA. Conduction resistance is L by Ka. Okay, but for cylinder, we have seen log of R2 divided by R1 divided by 2 pi Ka. So you will have to take care of that thing, the formula. So this formula is again given in page number 50. In fact, in page number 54, exactly what you see here is exactly given. 3 composite walls, so 3 composite cylinders, 3 wall resistances, 1 outside convection resistance and 1 inside convective resistance. So totally 5 resistances. The formula as you see here is given there in page number 54 of your data book. Then we have a important and an interesting concept called as the critical insulation thickness. Critical insulation thickness. See, many a times we insulate surfaces to minimize the heat transfer. Sometimes we insulate surfaces for the sake of safety purpose. That safety purpose is either to avoid a burn or to avoid some shock. So in such a case, when we want to avoid a burn, we put an insulation over that, but we also want the heat to be lost out, heat to be evacuated. Ideally, if there is no insulation cover, then the heat transfer will be maximum because there is zero resistance. But for the sake of safety, either to avoid burning or shock, we put in insulation. So similarly, we have electric cables. Electric cables, bare electric cable is a risk because electricity gives you shock. Therefore, we will have to cover it with some insulation. Insulation will protect you. Insulation on electric cable will protect you from shock. But then, as electricity passes through the cable, there is a heat generated, and that heat has to be removed. Otherwise, what happens if the heat accumulates? Then the heat will, in fact, melt the insulation of the electric cable, which is usually a plastic material over the electric cable. That insulation gets melted with excess temperature. So to avoid that, we have this concept of the critical insulation thickness. So here the critical insulation thickness meaning is different from what we generally understand from the insulation thickness that we normally talk about. Whenever we talk about insulation, we think that we are insulating to minimize the heat transfer. But when we talk about this critical insulation thickness, we are actually thinking about maximizing the heat transfer. So it's like an oxymoron. Why do we need insulation when we have to maximize the heat transfer? As I said, in some cases, insulation is needed for safety purposes, but still we want the heat to be removed. So that concept is what is called as the critical insulation thickness, which is that thickness that maximizes the heat transfer. Okay, so because of that, we have this concept. So we'll see what this is. In radial systems, now this particular concept is applicable only to radial systems. Critical insulation thickness concept applies to radial systems only. What are radial systems? Radial systems are either cylindrical or spherical, not a slab. So whatever critical insulation thickness we are talking about doesn't apply for a slab, but it applies for cylinders and spheres only. Why? We shall see shortly. So in radial systems, the conduction resistance increases with the increase of insulation thickness. The convection resistance, that this we know, the conduction resistance increases with the increase of insulation thickness. How? Because the conduction resistance is basically L by K, the general formula is L by Ka. The actual form will be different, but it is L by Ka for all things. So for conduction resistance, since the value of L is high, if the value of L is high, the insulation thickness will be high. But what happens? The convection resistance decreases with the increase in insulation thickness. What is the convection resistance? Convection resistance is 1 by HA is 1 by H multiplied by 2 pi RL. Okay. So what happens if R increases? If R increases, the denominator increases and the overall quantity, which is the resistance, convection resistance, will decrease. So what is happening here is, by increasing the resistance, as R increases, conduction resistance is increasing because it takes this formula, and convection resistance is decreasing because it takes this formula. So you see here, there is a because of change of one parameter, there are opposite effects on convection and conduction. So what is happening? If we continuously increase the insulation thickness, what happens? Conduction resistance increases, but convection resistance decreases. So that means there is a problem of optimization here. So we have to choose one value of R, one value of this insulation thickness, so that we have maximum heat transfer. So that insulation thickness is called as the critical insulation thickness. So you see here, optimum insulation thickness minimizes the heat loss. So remember, look at this wording. Optimum insulation is different from critical insulation. Optimum insulation minimizes heat loss. Critical insulation maximizes heat loss. So in the applications that I have mentioned, we need to maximize the heat transfer, but still insulation has to be done. So we'll have to choose an optimum insulation thickness. So you see here, there is a figure given here. In this figure, this is a, let us say this is the hot object, and this is the insulation over this hot object, hot rod. Over that there is this insulation thickness. So what is happening, as this radius increases, as this R of the insulation increases, the conduction resistance is increasing, but the convection resistance is decreasing. So this is represented pictorially later on. I'll show you that slide. So as of now, let us see how we can treat this with the concepts that are known to us. So now you see here, this is the Q dot. Q dot is the heat transfer. So heat transfer, we know it's the overall temperature difference divided by the total resistance. That is the standard formula. In this, what are the resistances? We have the outside convection resistance and the conduction resistance inside. Now we are not bothered about what is happening here as far as this critical insulation thickness is concerned, because our critical insulation is only from this point to this point. So we restrict ourselves to these limits. So outside there is convection, then there is a conduction resistance up to here. So let us not bother about the inside. Okay. Now the outside temperature, let us say this is T infinity, and the surface temperature on the inside, let us say this is Ti as represented here, Ti. So the overall temperature difference is Ti minus T infinity. So usually Ti will be greater than T infinity. So Ti minus T infinity. It's the overall temperature difference divided by the resistance. First resistance is by conduction, and remember this is a cylindrical surface, cylindrical shape. So for the conduction resistance of a cylindrical shape, this is the formula, log of R by Ri by 2 pi Kl. That's the formula. R is the any radius and Ri is the inside radius. Ri is the inside radius. And the convection resistance is 1 by 2 pi RLH. So on the outside, the convection resistance is 1 by 2 pi RLH. Okay. Now we'll simplify this equation and make it more general. So we define a new quantity, Q dot with a prime. You see this, Q dot and a prime. This is heat transferred per unit length. heat transfer per unit length. So we divide this quantity with L. So what happens is this L will get cancelled off, and if L is equal to unit length means L is equal to 1. So if we take L as 1, then that will disappear. So you see this term has taken a new form of this. Say very much same, except that there is no L here. Similarly, this term has taken this shape, no L here. Okay. So now we have this heat transfer per unit length is equal to overall temperature difference divided by the resistances, two resistances per unit length. So the first resistance is ln of R by Ri 2 pi k, and the second resistance is 1 by 2 pi Rh. Now, for, for this insulation to be critical, what we need to do is this total resistance should be maximum. If for optimum insulation, this should be maximum. R total should be maximum. Now, if we differentiate this resistance, what is the variable here in this entire equation? K is fixed for a given material. Heat transfer coefficient is fixed for a given flow conditions. So only R is the variable here. R. So we differentiate the resistance with respect to small r, which is the radius. So this derivative we equate it to 0. So differentiating this equation with respect to r will give you will have to be done. So on differentiation we will have 1 by 2 pi kr minus 1 by 2 pi r square h is equal to 0. So you have one equation here, and from this you can try to find out the value of r. So value of r is equal to k by h. Okay, so k by h is what is the value of r we have to choose. Now we have to find out whether this will increase or decrease the resistance. So will it maximize or minimize the resistance? That is something we need to check. So to check if the insulation thickness is maximizing or minimizing, we differentiate the r this value once again with respect to r. So d square r by dr square is what we evaluate. So we get this one, and at r is equal to k by h, if you evaluate this d square r by dr square, we get a positive quantity. We get this positive quantity. So from calculus we know that when this is positive quantity, what we get is the minimum value. So R total is the minimum at R is equal to K by H. So at this value we are having a minimum resistance. So for minimum resistance, what we have when the resistance is minimum, that means overall resistance is minimum, we will have the maximum heat transfer. So fortunately we are able to come up with an equation with a simple equation which will estimate what radius of insulation should be installed so that the person is protected from shock and from burn, and still the heat transfer is maximized. So this is called as the critical insulation radius. Remember, this is not the optimum insulation radius, it is the critical insulation radius. So for the critical insulation radius, the formula now is RCR. So until now we said it's simply R only. So now we have found that at this R, the total resistance will be a minimum, and therefore this R will now become the critical resistance. Critical resistance is K by H, and this will maximize the heat transfer. So this is what you need to understand. Now this particular figure will explain things much more clear. On the x-axis you have the radius. You see we have the radius here on the x-axis, R minus Ri. That means this is basically the insulation thickness. R is any radius, Ri is the inside radius. So R minus Ri will give you the insulation thickness. So on the x-axis you have this insulation thickness. On the y-axis you have the resistance. This resistance can either be convection resistance or conduction resistance. So you can see what is happening as R increases, as the insulation thickness increases, what is happening? The conduction resistance is increasing. It's increasing continuously like this. That we know. As thickness increases, the conduction resistance will increase. So as insulation thickness increases, conduction resistance is increasing. But the opposite is happening for the convection resistance. As the thickness is increasing, the convection resistance is decreasing. So initially when the thickness is 0, insulation thickness is 0, then the convection resistance is maximum, but after that the area is increasing because of this curved surface. Remember, for curved surface the area is 2 pi RL. So if R is increasing, the area is increasing, and the heat transfer area for heat transfer will increase, and therefore the convection resistance will decrease. Therefore, you see here the convection resistance initially at 0 insulation thickness, convection resistance is maximum, but as the area is increasing, convection resistance is decreasing. Now, if you add these two, conduction resistance and convection resistance, this is called as the total resistance. So this is what we have been evaluating. So this total resistance, if you plot against this R minus R1, you will see this kind of a behavior. So initially it is high, and then it is decreasing, and then again it is increasing. That means the total resistance is actually varying with the insulation thickness, and at one point it is minimizing. So this minimum value is the value at which we have this critical radiation insulation, critical insulation thickness. So at minimum total resistance, we will have the maximum heat transfer. So in case the two examples that I gave you, we will have to put insulation in such a way that the surface is covered, but still the heat transfer is more. But remember, this applies only for curved surfaces. Why curved surfaces? Because for curved surfaces, as the distance increases or as the thickness increases, the area increases. But for flat surfaces, see, this is the flat surface on which I am putting some insulation. I put some insulation here. The area is something. If I add more insulation, the area is still the same. Further insulation, the area is still the same. So the area for heat transfer is not changing in case of flat surfaces, but in case of curved surfaces only, area changes as the radius increases. Because of that reason, the concept of critical insulation is applicable only for cylinders as well as spheres. Okay, so now let us see where you can find. Now I want you to open your data books and tell me where you find this concept of critical insulation thickness here. I want you to tell me the page number. I want you to open the data book and I want you to give me the page number. You will find it in page 56 and also page 7. Page 56 for cylinder, in page 57 for sphere. So for cylinder, R critical for cylinder is the formula is K by H, and R critical for sphere is 2K by H. So remember, the formulas are not same for cylinder and sphere, they are different, so you need to keep this in mind. Now coming to this next concept called thermal contact resistance. What is this thermal contact resistance? Now until this point, what we have seen is whenever some surfaces are placed next to each other, you see this in this slide, cylinders A, B and C, they are different surfaces, but they are in contact, and we have assumed that the resistance is only because of this material thickness, and we assume that this contact does not offer any resistance. We assume that this contact surface is perfect and it hasn't got any resistance to offer, but that is not. We will have to consider that resistance also. So if we are going to consider that, you see here, whenever two objects are abutted like this, then if you take a closer look at the contact surface, you will find it like this. You see here, firstly the contact is not perfect. Both are not touching at all places. There are only few points of contact. Wherever there is a point of contact, you will have a conduction taking place, and whenever you have this gaps, and the gases that are filled in these gaps can either be responsible for some convection resistance, and also sometimes if it is hot, radiation resistance also. So basically you have in this contact points, you will have a complex uh, form of resistance, which is simplified by this concept called as a contact resistance. Okay, so in this contact resistance, we will have this heat transferred at the contacts and the gap and so on. So this is quantified by this Qx. So contact resistance is also available in the data book. I leave that for you to figure out where exactly. We've got few more minutes. Okay, so in composite systems, the temperature drop across the interface may be considerable. This is due to the contact resistance. So here we are considering this contact resistance. Surface roughness is responsible for contact resistance. When there is surface roughness, both the surfaces will not match and meet properly, and then contact spots are interspersed with the gaps filled with air. So heat transfer is due to conduction across the contact area and conduction and radiation across the gap. You see here this. There is a contact, so conduction resistance, and in these gaps, if the temperatures are high, then there will be radiation resistance also. And if the gap is big enough, there can also be convection resistance. Small gap, the convection is suppressed, but large gaps, the convection can also come. So this contact resistance is equivalent to parallel resistance due to contact spots. So you can see here, this can be represented as parallel resistance. So this is one resistance, this is another, all of them connected in parallel. So we treat them as resistances connected in parallel and evaluate accordingly. For rough surfaces, the resistance is mostly due to gaps. Okay, so the thermal contact resistance per unit area is given like this: TA minus TB divided by QX double dot. So in this way, we can evaluate the contact resistance is per unit area. Usually, the unit of resistance is Kelvin per watt, but for contact resistance, it is meter square Kelvin per watt. Sorry, watt per Kelvin. No, Kelvin per watt, and meter square Kelvin per watt is the unit for the contact resistance. That means Kelvin per watt means what is the temperature drop to transfer 1 unit of heat power. All right. So here is a summary of all the equations that we have, some of the equations, not all, but some of the equations that we have seen here. What is given is the heat equation for a plane wall, cylindrical wall, and a spherical wall. And for a cylindrical wall and a spherical wall, the critical insulation thickness is given. Critical insulation for cylindrical wall is K by H, and for a spherical wall is 2K by H. Okay, this you will find in the data book also. Then you have the temperature distribution. So if you know the end temperatures, you can find out the temperature distribution. So from these equations, I have shown you the plots. For a plane wall, temperature distribution is linear. For cylinder and spherical walls, it is non-linear. Then heat flux, you can calculate using this. And heat rate, heat flux is watt per meter square, and heat rate is actually watts. So these are the equations for that. And then thermal resistance also can be calculated using thermal resistance. For solids is L by cylindrical, slab is L by Ka, and for cylindrical wall is again basically L by Ka, but this transforms to log of R2 by R1 divided by 2 pi Lk. Similarly for spherical wall. So you don't really have to remember all these things, but just for convenience sake, I have put them together in one place. Okay, now we'll stop here, and in the next class, I will take up conduction with heat generation. So until now, we have considered one-dimensional systems with one-dimensional systems. Conduction, we have solved only the conduction equation. So convection we have taken care of using the electrical resistance concept. But what we have not considered is the heat generation and also the transient nature. of the problems. Transient nature of the problems we'll see in the next module, but heat generation we'll see in the next class. So heat generation is possible whenever we have systems like electrical conductors or nuclear reactors, which we shall see in the next class. Okay, so I'll stop here and let me take your attendance. Mrutunidhi?
Present, sir.
Abhilash?
Sir, Mritunidhi present, sir.
Yeah, okay. Abhilash present, okay. Dan Cherian?
Present, sir.
Now Dilip?
Present, sir.
Sir,
Madhusudan
present, sir.
Siddharth present, sir.
Srivatsan?
Present, sir.
Maitreyan?
Present, sir.
Lanivel?
Prashant present, sir.
Tamilalagan?
Present, sir.
Niranjan?
Present, sir.
Vaibhav Karan?
Present, sir.
Abhijit Menon?
Present, sir.
Pratik Krishna?
Present, sir. Present, sir.
Praveen?
Praveen present, sir.
Adil Sinju?
Present, sir.
Chaturvedi?
Present, sir.
Chintan?
Sir, Chintan present, sir. Chintan present, sir.
Hassan?
Come again, sir.
Hamza Hassan?
Present, sir.
Ayush Tripathi?
Present, sir.
Harshavardhan?
Present, sir.
Hemant Kumar?
Present, sir.
Shiva?
Present, sir.
Mauli Singh?
Present, sir.
Shubhavania?
Present, sir.
Sai Rohit?
Present, sir.
Raman?
Present, sir.
Lal?
Yes, sir.
Ish?
Present, sir.
Sudh Venkat?
Yes, sir.
Kumaran?
Present, sir.
Sundar Krishna?
Present, sir.
Present, sir.
Jayanti?
Present, sir.
Present, sir.
Badri Narayanan? Avito? Ajit?
Present, sir.
Harish Raghav?
Yes, sir.
Rahul?
Present, sir.
Nihar?
Present, sir.
Karthik?
Present, sir.
Gauri Shankar?
Present, sir.
Motishwar?
Present, sir.
Vijay Prakash?
Yes, sir.
Suja?
Present, sir.
M. Kumar?
Sir.
Karan Sarvesh?
Present, sir.
Ajay?
Present, sir.
Reynold Simon?
Present, sir.
Vamsi Krishna?
Present, sir.
Venkatesh?
Present, sir.
Jnanakshaya?
Present, sir.
Yes, sir.
Kiran Dev?
Yes, sir.
Varun?
Chat box.
Okay, I'll see that. Kunal Rao?
Kunal present, sir.
Na? Vedant Madhur? Anand?
Present, sir.
Vani? Vasan?
Present, sir.
Shankar Narayanan?
Present, sir.
Anish present, sir.
Santosh Raj?
Yes, sir.
Kumar?
Present, sir.
Akash Kumar,
Present, sir.
Prasanna,
Present, sir.
Kaustubh,
Present, sir.
Arun Ahalyan,
Present, sir.
Suresh Krishnan, Meena,
Present, sir.
Jafet Gionel, Manoj.
Present, sir.
I'll call the absent is Palanivel,
Present, sir.
Badrinarayanan, Avito,
So in the chat box.
Rahul, Varun, Vignesh Krishna,
Yes, sir.
Vedant Madhur, Shivani,
Present, sir.
Kalaipriyan,
Sir, replied in chat box, sir.
okay, I'll see that. Sarvesh Krishnan, Jafet Gionel, sorry, Jafet, okay.
Sarvesh also, sir.
All right, so we'll meet on Monday. We'll solve some problems on Monday, so come prepared with your calculators.